Right, and we are live. How are you doing, Andrew and Juha?
Doing great.
Very good, thanks. Yeah, good to
I
be
hope
here.
you are. Yeah, I hope you are as excited as I am for this one. This is something really special and unique for us, even if I say so myself.
I am truly as excited as a Finnish person can be, which would be like, I am excited about this.
You're at 100% there. No, I am particularly excited about this. We've been talking about this a lot for the last few months internally, so it's so good to get it out there and share it with the wider world.
Yeah, and just we are already seeing that the first people tune in. Thanks for being on time. But while we're waiting for the rest, I could say for you guys here that well, if you didn't already know, this is indeed a sort of a like a exclusive launch. So the people who are listening here are actually seeing this for like this, basically the first time ever in this setting. So this is still not yet publicly released stuff that we will be covering, and we will be only releasing this to the public later on. But so this is indeed the premiere of the process we are unveiling here. But all right, I guess it's time to get started. Let me just put on some introduction slides. I'll keep my section very short. But yeah, so just formally welcome everyone to our webinar, or actually not even a webinar, but the launch event for our AI plus multiphysics thingy. So we are indeed introducing, as we say, the new paradigm for engineering simulation. That's a lot to be said there, but we'll hope we can make up for it. So indeed, the main speakers for today are our CEO and co-founder Juha Riippi and our co-CTO and co-founder Dr. Andrew Tweedy, both of whom are familiar faces to from previous webinars here. So yeah. And here's the agenda for today, just a very quick look at it. So we'll kick off with Juha, who will be talking about, well, just introducing the process, the thing that we are releasing in a like a high level overview, and then Andy here will be going into the technical sort of introduction and the technical side of things, and we'll look at some real world case examples and some results there as well. And in the end, we'll conclude with a Q&A session where we'll hopefully address all the questions you guys have. And you can see the questions tab in the upper right hand corner. Now you can submit your questions there at any point during the show. We will be addressing them only in the last 15 minutes, but just so you don't forget them, you can be submitting them at any time. So without further ado, that's it from my part, and I'm happy to pass the mic to Juha.
Thank you, Jukka. So, welcome everybody on my behalf as well. As Jukka introduced me, I'm Juha, CEO and co-founder here at Quanscient, and really excited to be announcing some of the new capabilities we've been working on recently. Here with Andy, I'll keep it brief on my part, kind of more on the general benefits, the general process, the overview, listing some of the use cases that we've done, and Andy will then dive in deeper to some of the specifics and examples, so actually show you what can be done, what are the results, and how that all happens. But maybe before diving into that part, just covering a little bit of the philosophy behind this and how we arrived here, because basically when we're looking at a lot of the simulation workflows and simulation tools out there, simulation today is used mostly as a validation tool, meaning that an engineer designs something, they run a handful of simulations, and then they iterate until you have something that matches your specifications. And that approach is, of course, for historical reasons, that's why things have been done, but also technical limitations of the platforms out there. And with this approach, typically less than 1% of your design space ever gets explored. There's 99% of potential innovation that is left on the table. And that's exactly what we set out to change when we founded Quanscient. Instead of running a few simulations, what would happen if engineers would have the capability to run a few thousand simulations at the same time, starting to explore a vastly larger design space, arriving at unexpected solutions and converging on optimal designs faster than ever. And while doing that, we've been kind of working on this cloud simulation platform, but recently, of course, as everywhere else, a lot of AI methods have been emerging for simulations, and we have started to realize that actually the platform we built is a great source for training material for MultiphysicsAI, strongly coupled high fidelity data, and the ability to generate lots of that. And that solves one of the biggest problems in applying AI for physics simulations, which is the training data. Because unlike LLMs, where the whole internet could be your training material source, where do you find high quality physics data in the required quantities to train your AI models? And that's kind of led us here, where we see that the cloud solver we built acts as a strong foundation. It is the fastest, most scalable, strongly coupled multiphysics simulation platform out there, providing more than 1,000 times throughput, delivered by speed, scale, and flexibility. It's already proven at a lot of large enterprises. Some of the biggest R&D companies in the world are using our solution. And right now, we're building the use cases to use that data to train AI models, train neural networks and different kind of algorithms for even faster exploration at scale. And how this kind of works in the high level is that you create large quantities of proprietary training data, your data lakes to say, with simulation data, you train physics-aware neural networks, for example, being one technique, which gives you the ability to make quick decisions with full design space visibility, like good enough simulation results that are actually running on real time once you've trained these models, or in milliseconds. And as the last step, with the best pool of design candidates, you can still go in, verify those with deterministic numerical simulations faster than ever. And some of the use cases we've been working on, and the three first ones, the Piezo material characterization, which effectively solves an inverse problem for material parameters, the PMUT, so piezoelectric micromachined ultrasound transducer, sensitivity and bandwidth optimization, and microspeaker optimization are the ones that Andy, right after me, will cover in details. So don't go anywhere, you'll actually see exactly how it is done. In addition to that, we have an example on electric motor hub shape optimization and a piezo composite design that basically identifies best sets of designs instantly for this use case. And I think most of our audience is people working with simulations, working with engineering. So why this matters, what's the vision here, and what's kind of the in it for me? Well, we think kind of with the evolution of these more modern tools, any dollar you invest in R&D will come back multiple times in manufacturing costs, but of course also the biggest factor, shipping your product to market faster, saving time in engineering, building less costly physical prototypes. That's what it's all about, and reaching the actual optimal design faster than ever. And with that, I'd like to set Andy loose and show you exactly how this is done.
Thanks, Juha. Okay, so we've got a lot to cover. So let me dive right in. So as Juha said, we're going to cover some real technical examples of what we've been able to achieve so far. But I wanted to take a step back first and ask the question, why are we looking at AI and multiphysics? Why is this relevant? And then also ask the question, why is Allsolve such a crucial part of this, and indeed a great fit for advancing the ability to use AI in engineering designs? We'll go on to talk through 3 technical examples, each of which show off some unique challenges. And then we'll wrap up at the end and hopefully have some time for Q&A. So that important question, why AI? So we all know that engineers have pretty complex jobs and we get asked to solve very complex problems. And the challenge there is that it's often an inverse problem. Give me a design that meets this spec. Traditional simulation tools and FEM tools are included in this. They tell you what a specific design can do, how it will perform. So as engineers, when it comes to exploring a large design space, we're often left on our own, and it can become a very iterative and costly process, both in terms of number of simulations, but also in terms of engineering time. And the other thing is that if we're honest, we don't want to just find one so-called optimum design. Ideally, we would like to have visibility on all of the best designs within a given design space. Now, AI can help us do that when provided with rich multiphysics simulation data. It can help quickly identify design candidates and clearly visualize some of the important trade-offs. And on top of that, it can give us some indications as to how robust a design is. We've got some examples of that here as well. But just to keep things conceptually simple at the start, let's think about something that we probably all have an intuitive feel for, a car engine. It's a classic engineering trade-off. Do we want a very efficient design, or do we want a very high power output design? And we intuitively know, just based on our experiences in day-to-day life, that there's a trade-off along there. We don't encounter car engines that are up in this top right corner, which is ultimately where we would like them to be. So we make some sort of choice between the best efficiency or the best power. And in most cases, we end up with some sort of compromise. So as a concept, when you approach an engineering design, wouldn't it be great to be able to visualize this curve for your specific problem, to be able to find it quickly, and then to be able to discuss all of these design options with your colleagues in design meetings? So that's a high level goal that, as Juha said, we're setting out to do. How can we enable more innovation? How can we make it easier to explore these spaces? Okay, so that's the problem. Why is Allsolve potentially a fit? Well, Juha already touched on many of the points. We are a cloud-based, cloud-native solution. We are a finite element method solver, and indeed we are inherently multi-physics. So we have strongly coupled multi-physics. It's incredibly scalable, so we can parallelize problems across many, many CPUs, potentially thousands of CPUs for very large problems. We can run them very quickly. And on top of that, due to our cloud flexibility, we can allow users to run many hundreds or even thousands of simulations in parallel. So when we think about the challenge of creating feature-rich multi-physics training data sets, Allsolve is ideally positioned to be the engine for this. So what might this look like from a high level? Well, Allsolve is able to run many, many simulations, and that can potentially create a large data set, which we can then use to train machine learning algorithms or other approaches. And we can train them to do some of the higher level tasks that we're interested in. That could be anything from acting as an AI surrogate model for the FEM simulation, which can be executed very quickly, or it could be tackling higher level tasks, which we'll touch on as well. So we can produce a data set, we can conceptually train an AI model on this. There's a couple of potential ways of doing this that we're going to see here. One approach, which we would call the forward model, is to train an AI model to be a surrogate for the FEM simulation. So accept design variables as inputs and predict key performance indicators, or essentially outputs. But we can also flip that around. We'll see that in one of our examples. We can train an AI model to look at the outputs of simulations and give us information on what the inputs were. And in some circumstances, that can be a very powerful method to directly solve inverse problems. So you have already mentioned some of the problems that we're working on. That's great, because I don't need to talk in detail about them here. The one that we're going to really use to illustrate this whole process is the PMUT design example, where we use AI to optimize an ultrasonic PMUT sensor. And then we're going to talk for a little bit about a MEMS microspeaker design, which we've produced some really interesting outputs from a manufacturing engineering perspective, looking at design robustness. And then finally, we're going to touch on a material characterization problem, which is a great example of this inverse problem solution that I just mentioned. So starting with the PMUT, PMUT stands for piezoelectric micromachined ultrasonic transducer. It's a type of ultrasonic MEMS device, and it's found increasing use recently in everything from biomedical ultrasound to wearable devices, games controllers, a whole range of things, industrial sensing, to name a few. And this is just a quick snapshot of a really basic PMUT example within Allsolve. So here you can see our user interface. You can see a simple, what we would call a unit cell model of a PMUT. It's actually modeling 1/4 of a circular PMUT cell. We've got an elastic layer, we've got a piezoelectric layer, some electrodes, and a water load below it is the large blue region here. And you can see some of the physics that we're simulating here. So if we run a simulation of this in Allsolve, we can produce a wide range of really useful, we would say, feature-rich results. And the one we're going to focus on today is the transmit sensitivity spectrum. That's what we see on the left here. We can also calculate things like electrical impedance, but we're not going to spend any time on that today. The two things we're going to focus on here are the transmit sensitivity, that's how high is this peak, and the bandwidth, which is how wide this is. And this is somewhat related, if we think about the medical imaging case. The transmit sensitivity has an impact on how deep into the body we can image. It ultimately contributes to our signal to noise. And the bandwidth contributes to our axial resolution, and ultimately is one of the things that governs how high resolution our images can be and how well we can differentiate between tissue structures. So these are really important things. Unfortunately, they're a little bit like power and efficiency in the automotive engine example. We know intuitively that they have to be traded off against one another. So it's an excellent test for how we can use AI in a design space application, exploration, sorry. So we've picked 4 design variables. They're all dimensions of this PMUT structure that we might want to optimize. And we've picked 4 key performance indicators, 4 KPIs that we're interested in studying. And our goal is to maximize both the sensitivity and the bandwidth of the device. So the first step in that process is to generate a large data set. So we ran 10,000 versions of this PMUT simulation, each with randomized dimensions. So each of those 4 input variables was randomized. Simulation time, these are really efficient models. So we can run one of these models in around 5 seconds. We can execute these design studies in parallel. So we can create data sets like this very rapidly in Allsolve. And even once you've produced this raw data, you can see from looking at the cross plots, either between inputs and outputs, or in this case, between the 2 outputs, that there's already some interesting trends in the data. So there's clearly some information in here that might guide us in terms of design. The question is, how do we use that? How do we distill useful knowledge from that? And that's where the AI component of this piece comes in. So we can train an AI surrogate model to look at the design variables and predict the 4 output KPIs. This is possible in around 5 to 10 minutes on a modern GPU. So it's not a particularly heavyweight training operation. And the result is quite a lightweight algorithm that we found for most of these problems to be accurate to around 1% and executes in well under a millisecond. In fact, we can run hundreds of thousands of inferences per second. So the potential there is that we can do some things in real time that previously took a long time to do. And one of these is to calculate this performance curve, exactly like the curve that we talked about on our automotive engine example. There's a name for that curve, which is the Pareto front. It's the set of Pareto optimal designs that are not dominated by any other solution. And actually, to improve one of the objectives, you by necessity have to reduce the other objective. So it's a way of expressing the set of best possible designs. Now, traditionally, to do this, it's an optimization process, and it often takes tens or even hundreds of thousands of function calls, and they're quite sequential. So to do this with an FEM algorithm, for any of you who have worked in multi-objective optimization before, it's a very expensive process. By plugging in our AI surrogate model instead of the FEM model, we can run this operation essentially in real time, and we can calculate a Pareto front like this for our PMUT design in 1 or 2 seconds. So what you see here, again, think just back to the engine example we plotted at the start, but in this case we have fractional bandwidth on the x-axis and sensitivity on the y-axis. We'd ideally like to be up in this top right corner. And to really illustrate what's happening here, we've plotted the training data set as blue dots. And you can see that there's heavily weighted to here. There's some areas that are sparsely populated. Now, what's really interesting is that our Pareto front is quite separated from the bulk of this data. It's identified a bunch of designs that we'd be very unlikely to stumble across by chance or in a very sequential iterative process, manual iterative process. So the first question we have to ask ourselves is, are these real designs, or is there something, are they perhaps AI hallucinations, or perhaps just maybe inaccurate predictions? The good thing is in Allsolve, we have a very rapid parallelized simulation platform. So we can very quickly run, in this case, there are 600 dots, 600 designs along that Pareto front. So we have run 600 validation simulations here. And the answer is yes. These designs appear to be real. For each one of these, there is a real geometry and a real set of outputs. So very quickly, we've gone from an AI-generated front to a set of simulation data that we can have a lot of confidence in. Now, the very astute amongst you may realize that we've asked this algorithm to optimize 2 outputs, sensitivity and bandwidth. We didn't constrain anything. One thing that we did not constrain was the center frequency where our PMUT is operating. And any of you who are familiar with ultrasonic sensors probably know that that's usually one of the first things we specify. We might want a design to be centered at 12 megahertz, for example, somewhere in the middle of this plot. So the algorithms found the best possible designs, but regardless of center frequency. So one of the questions is, well, do we have to go back to the start and repeat all of this? And the really powerful thing about this is, no, we don't. We can apply constraints in this Pareto front exploration, both to design variables, but also we can constrain KPIs. So in this case, we can go back and impose a constraint that the center frequency should be 12 megahertz. We can recreate this red Pareto front in a matter of seconds. And when we run the validation sims, we once again confirm that these are real designs. And what's really nice is we now have a line of designs that are all potentially options for our 12 megahertz PMUT project. We can sit in a design meeting and we can debate where on this curve do we want to be most competitive in the market. So a huge step forward in terms of having data available And as one example here, this was my original PMUT example. We can see that applying this process to it immediately found a series of better designs. If I wanted to choose, for example, 100% fractional bandwidth, we could pick a design here. And this is how it looks compared to the original design I showed you. It's not only improved both of these outputs, excuse me, but we've also adjusted the center frequency to our design spec. So we've achieved three things in one here very rapidly. So hopefully that gives you an in-depth snapshot of the process and what is possible. But I wanted to pick two other examples to showcase today that also show some of the other things that are possible. So this example is another MEMS device. It's a electrostatic microspeaker, and it comes from this excellent paper. We've shown this device, in a few webinars already. It's a great example of the type of multi-physics problems that we excel in. There's a lot of things happening here. We can capture all of that in a coupled solve. And I'm actually going to skim over a lot of the details in here. Essentially, what we're trying to do with this design task is to maximize sound pressure level, so the loudness of the microspeaker, and we're trying to minimize total harmonic distortion. So any audiophiles amongst you will be very familiar with these two things. And can we use a similar approach to what we just shown with the PMUT to achieve this? And the answer again is yes, we can. So this is a plot of sound pressure level versus total harmonic distortion. In this case, we want to be up in this corner where it's loud and the distortion is low, so our audio quality is good. The blue dots here are the training data, and the one highlighted here is actually the initial design that we've used in some previous examples. What this AI-based Pareto front exploration was able to do was identify a bunch of designs, potential designs in red here, and indeed we were able to validate them with an Allsolve simulation for each. A little bit more of a gap here compared to the previous example. So all of these details will depend on the amount of training data generated and a lot of problem-specific things as well. But we were able to maintain and slightly reduce total harmonic distortion whilst also producing a 30% improvement in sound pressure level, which is a huge design achievement. But one of the reasons I really wanted to show this example to you was that this type of AI-based surrogate model isn't just useful for design exploration, it's also a very powerful tool to explore design robustness and manufacturability. So what we have here is, think of this scatter plot, or each of these scatter plots, as a two-dimensional histogram. They're a little bit like the cross plots I showed earlier, but they show how total harmonic distortion and sound pressure level vary if we, for a given design, if we alter some of the dimensions of the device over a normal distribution. So think about this as we have manufacturing tolerances, and we want to know if, with a given set of tolerances, what the distribution in performance will be. And with the AI surrogate model, we can assess this in seconds rather than having to run a lot of full FEM models. And indeed, we can take this a step further. One of the things we wanted to showcase is how this could be used for looking at manufacturing yield. So here we've put pass-fail criteria on both total harmonic distortion and sound pressure level. The green green geometries will pass. The ones falling outside in the red areas will fail for one or both criteria. And on this plot, we can see how yield will vary based on where we set the tolerances. So there's a huge, rich amount of data that suddenly becomes very accessible to manufacturing engineering teams by having these lightweight AI models available for your designs. So one final thing I wanted to highlight is something that is a little bit different. This is a material characterization problem. So we've looked at two design exploration problems that used an AI forward model as a surrogate for the FEM simulation. Here we're going to take the opposite approach, where we train an AI algorithm to look at experimental data, essentially outputs, and predict the inputs. And the inputs that we want to predict are material properties. So a problem that I'm very familiar with my time in ultrasound is that for piezoelectric sensors, piezoelectric materials are incredibly hard to characterize. It's an industry-wide problem. For piezo materials, there are a minimum of 12 unknowns due to their anisotropic and their piezoelectric nature. And characterizing these from first principles is a very expensive, time-consuming process, to the extent that not many companies undertake it. And the downside of that is that if you don't know your material properties well, it becomes very difficult to run accurate simulations, and therefore it becomes very difficult to predict what your prototypes are going to behave like. That becomes a very expensive process. So as an example, what we chose was a simple bulk PZT disk that supports both thickness vibration modes and radial vibration modes. And experimentally, if you measure this on an electrical impedance analyzer, you can pull out the electrical impedance and you'll see some quite a complex spectrum that relates to the radial mode behavior and the thickness mode behavior, all the overtones of both of them, and unfortunately they all interfere with each other. It's a really complex data set to interpret from first principles, but potentially an excellent data set to apply deep learning to. And that's exactly what we did here. We randomized not just material properties, but we also randomized the disk dimensions. And we created a large data set of 10,000 Allsolve simulations. We then trained an AI algorithm to look at the impedance magnitude and phase and use this to predict the stiffness matrix, the piezoelectric coupling matrix, and the permittivity matrix of the material. We spent some time testing this in a little demo user interface where we used randomly generated simulated piezo materials as an input, and we passed them into our AI model. We asked it to produce predicted values for each of these material properties, and then we compared its predictions to the actual properties used in the simulation. And what we observed was error rates significantly less than 0.25%. Essentially a very promising technique for characterizing these types of materials. Now, we have a big user base that uses piezoelectric materials in MEMS and spilling out into other applications. So we're actually developing a beta feature where this is built into Allsolve. When you go to create a new piezo material, you have the option to use AI to do it. You can input an experimental data set along with its dimensions and weight, and the AI produces a custom material set for that material. And this is something that our customers are already starting to experiment with. So those are the first problems that we wanted to showcase as part of this session. I realize we're getting towards the point where we want to open up for questions, but I wanted to bring some final thoughts. And going back to the car engine example, I wanted to show how this potentially can be used as a design develops. So we start off with the initial red curve that we had. That represents what our original technology can do. But as we make new innovations, maybe in this case, we try different fuel types, different engine layouts, we can potentially identify improved designs or potentially alternative technologies that address a particular area of this curve very well. But as a call to action, what I would like to really throw out to you is how can we use this to identify the designs of tomorrow that are really going to offer a step change in your area. And I know that Yuka has the magical ability to introduce polls. We thought that this might be a good chance to throw up an option to vote. So would you be interested in getting in touch with us to explore how these technologies could be used to improve devices in your application? I think Yuka's going to open that up just now.
Indeed. Yeah, it should be visible to everyone on the screen right now. Thank you, Andy and Juha, for the great presentation so far. We already we can let this poll stay here for a while. We have received quite a lot of very great questions already, but already at this point, feel free to just keep them coming. So we'll use at least the remainder of our time to cover as much as we can. And for the ones that we don't have time to cover live, we can and we will follow up with the people in specific. So follow up on with email. So just closing the poll in about 10 seconds or so. So just the final answer still. Of course, you can always reach out to us in any other way as well. LinkedIn for literally any three of us. Email, any way possible. But this is just the easiest way to let us know that, so that we'll be in touch with you. But all right, let's end the poll there and jump right into the questions. So the very first question, I think that was somewhat covered, just to make sure. So how do you check the accuracy of the simulation model? So I think that was pretty well covered. So yeah,
I think it's the absolute relevant question, particularly anytime you're using new techniques like this. How do you verify accuracy? So running an FEM simulation as a ground truth is absolutely the way to do that. We make that very easy. And as we develop these tools into our user interface, we want to make it super easy to say, hey, here's my predictions. Can you please validate them? So that's a workflow that will be built in.
All right. Then there was a somewhat specific question. I hope it goes or relates to or many people can relate to it. So there was a question on, can you simulate nonlinear structural mechanics that involve complex contact and large deformations?
Yes, we're doing a lot of work on contact at the moment. It's something that we've put a bit of focus on this year. So yeah, that's something we can handle.
All right. Then there was a question on, what mechanism does your model use to prevent the generation of non-physical solutions?
Again, very relevant. I think that's something that you need to look at on an application to application basis. So with any of these AI training examples, you need to consider how do you constrain that problem. So one of the things, one of the methods is to create the training data set such that all of the designs within that are sensible, potentially manufacturable, and then to only ask for AI predictions within that range. And the workflow that we showed does exactly that. But a little bit like the frequency constraints that we showed in the PMUT example, you can go back and say, from a process point of view, I don't really like having this layer as small as 100 nanometers. I would like to keep it above 500 nanometers for some production reasons. You can go back in, you can recalculate your Pareto front based on those constraints. So we've put a lot of thought into that. There's still a lot of flexibility with how you do it, and that's by design. But yeah, very relevant question.
Right. The next question, as I understand, has two parts. So, are you able to train your surrogate model on external data and predict result fields instead of KPIs?
Again, these are things that have come up. So good question. External data. External data isn't actually something we've explored. We'd be open to understanding what your thoughts are there and how our Allsolve data could work with potentially experimental data in one training set. So these are things that could be of interest. The second part, remind me on that, Yuka.
So on the result fields instead
Result,
of
yeah,
KPIs.
So far we've focused in these examples on scalar KPIs, but yes, we believe that producing more data-rich potentially fields, but one of the things we're initially going to look at is maybe result spectra. So can we produce that transmit spectrum or transmit receive impedance? So we've approached this from a very incremental kind of hypothesis. We've started with scalars. We're going to move to maybe producing some spectra, for examples. And we definitely believe there's ways of producing full fields. It does make the AI piece of the problem more complex, but it's definitely extensible to that. And there's several techniques that we're looking at to reduce the training time and the data requirements for those types of problems.
The next question has, well, there's also, again, two parts to it. And the first one has some context. So it goes like this. most FEM simulations don't work because of many things like we, the user, forget to set up something properly. So how do you know that the FEM simulation results you're using as training data are good or make sense, especially when you're trying to find the best design for an already complex geometry with several layers, materials, shapes?
That's exactly the way that, from engineering principles, we should look at any of these problems. So it's important to measure real devices. It's important to compare to experimental measurements, to analytical models from the literature. Nothing that we've presented here today is to say that there should not be rigor and engineering thought going into setting up the models. And that's something that we work with our customers to help them to achieve a good fit and a good a model that captures the real device behavior well. So that is well worth pointing out. I appreciate it being asked, and should be a real pillar for any of this additional work that we've shown here.
Yeah, and the other question was, and I spotted at least another one on this sort of topic. So the question was, if the AI is going to look at 1000x and more possible designs to find the best one, how does this work in terms of core hours? Again, when considering that we want to find the best design of a complex geometry.
Yeah. So the examples I showed here used around 10,000 designs or simulations in the training set. We've experimented with using significantly less. So there's definitely a lot of flexibility as to how much data you want to provide. It really comes down to trading off data set size and accuracy. Sorry. I think taking the PMUT example as the main example here, I think the training cost for that was around 30 to 40 core hours. So really pretty insignificant. I think it's maybe getting into a little bit much detail to talk about exact pricing models, but in short, our model is that core hours, compute hours should be cheap. We want people to be able to run lots of simulations like this. So nothing that we've shown here is cost prohibitive. It's definitely not a bottleneck in the problems that we've explored here.
There was a quick question on any superconductor applications.
Yes, we've not shown any examples here, but this has come up both in discussions with existing superconductor customers and also our internal discussions, as our team has pretty significant expertise in that area. So one area we're interested in is material property homogenization for superconducting tapes. The potential to back out AI properties for a homogenized tape in order to make the FEM model much lighter weight, be able to look at more macroscopic structures without having to mesh the fine details of the tape. So that's something that we're hoping to put some work into. And of course, we already have customers using AI to explore superconductor design spaces. So that's an area that we're interested in building out examples as we move forward.
Then there's a very relevant question. So is the software, and I guess this could be split in two. So talking about the software Quanza and also and then separately the multiphysics AI. So is the software plug and play? So is it intuitive or does one require specialist training to use it?
I think, yeah, I would answer yes. We feel like we have one of the most intuitive FEM, general purpose FEM packages. I would always say that the engineering simulation tools do need some training and some support, and that's what our engineering team is here to offer. So we typically work quite closely with our company, with our customers. But I think one of the advantages that we have with our platform is we're cloud native. So our interface is web-based. It really lends itself to intuitive point and click setup. Were you gearing up to say something there?
You covered it well. So yeah,
Okay.
that's of course one of the big advantages. That installing no packages, configuring your IT clusters, and
Yeah.
things like that. So ease of use in that sense is really you can just start using the software with a lot of compute resources.
And was there a second part to the question
Yeah.
that
So
I didn't
the
quite
second
cover
part
yet?
was likely on the multiphysics AI part. So can a user
Of
just get
course.
started with that?
Yeah. So that's something that, as you have said at the start, it's not integrated into our tool at the moment. We have a Python-based SDK where users can call our solvers. So you can have your local Python environment calling many thousands of Allsolve models, which can run in parallel through our Python interface. And a lot of the examples that you see here were built using that. So a local Python environment calling Allsolve for training data and using PyTorch or TensorFlow or your favorite ML environment to train the AI models. So it's a very open system from that perspective. We do plan to build functionality into our tool because we realize that engineers aren't all AI experts. Certainly, if I were using this day to day in a design job, I'd want these workflows to be simplified, to be very accessible, and we think that will be very attractive to our users. So that's something we're working on.
So we have time for a couple of more questions. First one could be about it seems like this user might have had a slight misunderstanding, but I think it's good to address here. So the question goes, could you touch upon data privacy / leakage when using already generated training data?
So I can also cover this. So to be clear, that we never use models to kind of generate pre-generated training data. So if you're running your simulations, you own that data, and that your models can be trained for your purposes. What we are, of course, working on is some of our internal demos, some of the kind of that are already out there in the public space that we can train more general models based on that. But your data is your data, and also the surrogate models that you train are kind of within only accessible for you.
All right, let's see. There's whole bunch of questions here that will unfortunately go unanswered live here. But as said, we will be answering each of these questions to the people individually, and for the questions that serve a general purpose as well, and could have general value, then we will be answering those live. Let's see. There's last question, how many objectives can you specify in the multidimensional optimization?
Yeah, well, that's one of the areas where it becomes very powerful. I think as design problems get larger in terms of the dimensionality. That's where traditional approaches tend to break down, because the design space just becomes so big. So I think we've certainly experimented with 6, 7, 8 design variables. You know, very large space, but there's not a fundamental limit. You just have to bear in mind that as you add new design variables, you're increasing the space quite dramatically. And while AI, particularly neural networks, are particularly effective at learning these problems, the bigger you go, the more data that you're going to need to put in to make things work well. So it's a trade-off.
All right. Well, I see that the time has hit the hour. So just to be respectful for everyone's time, it's time to wrap it up. So thanks again. Thank you, Juha. Thank you, Andrew, for the amazing presentations. Thank you all of you for joining. And
yeah,
Juha,
thank
Andrew,
you to
please.
the audience for some excellent questions there as well. That's
Yeah.
been some good discussion.
All right. Well, hope to see everyone again on a later time. And thanks once again, and have a great evening. Bye-bye.
Thank you, everybody. Bye-bye.
Thanks. Bye-bye.